Chapter 6 was where we studied chemical reactions. We started off by looking at how to balance a chemical equation and what that meant. In the context of conservation of mass, whether it's a chemical or physical change, but we did focus on chemical changes in this chapter, we're doing nothing more than starting with some number of atoms and ending with the same number of atoms. If it's a physical change, we're moving them further apart or closer together. If it's a chemical change, then the atoms are unbonding, rearranging, and rebonding with new atoms. But the most important thing is that I'm starting with the same number of elements on the reactant side as the product side. And that is what balancing an equation is going to accomplish for us. It's going to help us conserve mass in the overall chemical equation. So remember, we said that we don't want to change subscripts. If we change subscripts, then we are changing what the chemical formula is. So we want to change the coefficients. So let's see, if we're looking at this equation, I have 3 sodium on the reactant side, and I have 1 on the product side. So I'll start by changing that coefficient to a 3. But I see I have 2 phosphates on the product side. Place a 2 there to make that 2. That changes the sodium to 6. So I'm going to go and change that again. And then I see 3 magnesium on the product side, and I'll make that coefficient a 3. So that should balance the equation there. In this type of reaction, one of the things I said may be helpful, we could have used in the first one too, like if I see a polyatomic ion like phosphate on the left and right hand side, count it as a whole unit. Don't split it up and say I have this many phosphorus and this many oxygen. Say I have this many phosphates on one side and this many phosphates on another. If I see an element that's split amongst a few different substances on one side, like I see oxygen split up between water and carbon dioxide here, we should balance that last. So we'll balance the carbons first. Do that by placing a 3 there. Then I'm going to balance the hydrogen by placing a 4. Now I can add up my oxygens. I have 6 from the carbon dioxide plus 4 from the water. That's 10 total. So a 5 there will balance the oxygen. Right. Then we went into the different types of chemical reactions. The first we looked at was synthesis, where we have 2 or more, I should say, simpler substances that are coming together to form one single compound. An example might be aluminum plus chlorine turning into aluminum chloride. Now, a couple of things to keep in mind. Phase of matter, which we should know. Formulas for elements, whether it's diatomic or not. And then in order to figure out what the formula for the product is going to be, we have to think about bonding, right? Aluminum and chlorine are going to bond ionically, which means they're going to turn into ions, which means the ions have to follow the rule of 0 charge. Al is +3, Cl is -1. Ionic compounds are solids. And then we go back and we balance the chemical equation to conserve mass. In another example, if I have nitrogen gas plus hydrogen gas, they're not going to bond ionically, they're going to bond covalently, and that goes back to following Hank, right? In terms of the electrons that they're going to share. So nitrogen will covalently bond 3 times, each hydrogen will covalently bond once. We get NH3 there. Again, balance the equation to conserve mass. Decomposition is the exact opposite. We start with one compound that's breaking down into simpler substances. Could be simpler compounds, could be elements, could be a mixture of the two. We really looked at splitting up a binary substance. So let's say water can only split up into hydrogen gas and oxygen gas. Again, emphasis on writing the formulas correctly, phase of matter, and balancing the chemical equation. We looked at some specific types of decomposition. You can go back and view the specific examples we looked at in our notes, but one that comes to mind would be like decomposition of a carbonate, for example. So something like sodium carbonate will decompose to give us a metal oxide. So that's sodium oxide plus carbon dioxide gas, right? So there were some specific decompositions we looked at. Single replacement is where I have an element and a compound where I have the element swap places with another element in the compound to get a new element and a new compound. We use the activity series to help us predict if these reactions would occur, because not all of them do, right? Going back to stability. I gave us a sample activity series here. Now, generally, it's not perfect in terms of the order from top to bottom, but it's generally the group 1s, then group 2, then aluminum, then the transition metals, and the coinage metals. And those are the only examples you're going to see, right? Without the actual table to use to see where the relative positions are, it will be obviously occurring or not. So I'll give you an example. Like if we looked at sodium metal and magnesium chloride in a single replacement reaction, let's make it a solution of magnesium chloride, then what I'm looking at here is sodium's a group 1, magnesium's a group 2, sodium being in group 1 should be able to replace that magnesium. So we're going to get the new compound to be sodium chloride, and the lone element now is magnesium. And then we balance the reaction to conserve mass. If it was the other way around, magnesium plus sodium chloride, we'd predict that it probably won't happen, right? Because magnesium is less active or less reactive than sodium. And we talked about redox in this chapter, and we're going to review that next. But ultimately, the stability piece here has to do with redox. Which element is more likely to oxidize or reduce? So in this case, the reaction that happens, the sodium is more likely to oxidize, where the magnesium is more likely to reduce. So that is what happens. The sodium would rather exist as an ion, where the magnesium would rather exist as the atom when placed next to each other. For a double replacement reaction, this was all about whether or not we were forming a precipitate, so we have to know our solubility rules. So let's take sodium hydroxide plus copper 2 nitrate. Now with this, we can't predict whether or not it will happen just from the reactants. We have to predict what the products will be. So my two possible products are going to be sodium nitrate, which has the formula NaNO3. Remember, charges and rebalance to 0 if you have to. And then copper 2 hydroxide. This reaction happens because the copper 2 hydroxide is a precipitate. The sodium nitrate will form and will just dissolve in solution. We don't see it forming as a solid because the whole thing's happening in water. Solubility rules we need to know, right? Hydroxides are generally insoluble unless they are one of the hydroxides on what we call the big B, which was group 1 and then several of the group 2 elements. All other hydroxides are insoluble in water. If in a double replacement reaction we predict the two products and they're both soluble, then we would observe no change. And if we're observing no change, then therefore no chemical reaction occurred. The last type of reaction we looked at was organic combustion. And this was like the example above. I have a hydrocarbon that's reacting with oxygen, or an alcohol or an acid that's reacting with oxygen to form carbon dioxide and water. As long as it's an organic molecule that contains carbon, hydrogen, and or oxygen that's undergoing combustion, the products are always going to be the same, CO2 and H2O. And the balancing order to make your life easier, carbon first, hydrogen, and then save the oxygen for last. We looked at redox, or oxidation reduction reactions. Some of the reactions that we've looked at already can be classified additionally as being a redox reaction. Some are not. But if we are classifying something as redox, we're saying that in the process there's oxidation and reduction going on. What is oxidation and reduction? Oxidation means that something is losing electrons. The oxidation number is increasing or becoming more positive. The electrons are a quote-unquote product if we're writing a half reaction to show that they are being lost. And the substance that is undergoing oxidation is known as a reducing agent because it allows reduction to occur. Oxidation and reduction have to occur together. So for something to lose electrons, something has to gain them, and vice versa. If something's undergoing reduction, that means it's gaining electrons, its oxidation number is decreasing or becoming more negative. The electrons are a reactant in the half reaction to show they're being added or gained. And something that's undergoing reduction is known as an oxidizing agent because it allows oxidation to occur. Both of these occur simultaneously. You'll never have one without the other. Single replacement, synthesis, and decomposition are almost always redox. Double replacement is never redox based on how the oxidation numbers or charges change. Now, oxidation numbers similar to charge and in some cases the same. We said for something ionic, and the oxidation number is the charge. But for something that's molecular covalent, there is no charge, but we can pretend there is, and that is exactly what the oxidation number is. For something ionic, it's its charge. For something molecular covalent, we're pretending it's ionic, assuming the electrons belong to the most electronegative element, and then seeing what the quote-unquote charge would be. That's the oxidation, and it's used to keep track of electrons in redox reactions. We went over some rules to help assign oxidation numbers to elements in a certain species. Free elements have an oxidation of 0. Group 1 always have an oxidation of +1. Group 2 elements always have an oxidation of +2. Hydrogen has an oxidation of +1 when it's with a nonmetal, but -1 when it's with a metal. Fluorine's always -1. All of the other halogens are -1 except when they're with oxygen. Oxygen's typically -2 except when it's with fluorine, which is always -1. If it's with fluorine, it'll be +2. Or if it's in a peroxide, it's -1. The most electronegative element, when all else fails, if we have no more rules to use, the most electronegative element will have an oxidation that equals its charge as its most common ion. Some of the oxidation numbers must equal the sum or must equal the overall charge of the species. If that's a compound, it's neutral. If it's an ion, it's the charge of the ion. And then use the charge of the polyatomic ion to help find the charge of the metal ion if we're talking about an ionic compound, especially if it's a transition metal. And we'll go over a couple of examples to show you what that looks like. So both chlorine and sodium in this example are 0 because they're a free element. They have not combined with anything yet, so they haven't lost or gained electrons. In this case, oxygen is -2 and sodium is +1. Chlorine's a halogen, is always -1 except when with oxygen, but that's not the case here. Magnesium is group 2, so it's +2. Fluorine's always -1. Oxygen, typically -2, but it's with fluorine in this case, +2. And it makes sense, +2, and then I have 2 -1, so that adds up to 0. Calcium's a group 2, that's +2. Nitrate has a charge of -1. Oxygen is always -2. That means nitrogen must be +5 there. We could add up the sum of the oxidations in nitrate to get prove that our overall charge is -1. Or if we throw it back in the compound here with calcium, we'll see the overall charge of calcium nitrate should be 0. So either way we want to do it, we should get the same thing. In this compound, I have copper, which is a transition metal. I'm going to use this rule to help me here. I know that chlorate's -1, so that means the copper must be +1 here. Oxygen's -2, and that's -6. +1 would be -5, so the chlorine here must be +5. Potassium is +1, always. Oxygen's -2, that means manganese must be +7. And then silver is +1. We could figure that out because phosphate's -3. Oxygen is -2. That means that phosphorus must be +5. So that's how we can use our rules to help assign oxidation numbers in certain species. And ultimately, we are assigning oxidation numbers so that we can look at the oxidation numbers before a reaction and look at the oxidation numbers after and see did any increase or decrease, so we can know which species underwent oxidation and which underwent reduction. For half reactions, let's say aluminum here, it looks like it's undergoing oxidation. So losing 3 electrons, so it's going to turn into Al +3. The copper +2 ion is evidently undergoing reduction, gaining 2 electrons to turn into copper 0. And the chlorine here, we have to think about this for a minute, loses 1 electron to turn into Cl0, but Cl0 doesn't exist as monatomic Cl, it's Cl2. We have to balance the equation for mass and then charge. So 2 chlorine ions lose a total of 2 electrons to turn into a molecule of Cl2. For balancing redox equations, we can assign oxidation numbers here. Tin is +4 here, nickel's +2. We can write half reactions. So for example, nickel 0 is oxidizing to turn into nickel +2 by losing 2 electrons. And tin +4 is gaining 4 electrons to turn into tin 0. And then what we want to do is make sure that the number of electrons lost equal the number of electrons gained. So I'm going to multiply that equation by 2 to get 4 electrons. My electrons lost equal my electrons gained, and when we add them together, then we get this overall net ionic equation. Now, net ionic equations can become a little bit more simplistic. This was sort of given as a net ionic equation already, but we could be given a molecular equation, right, which is our complete equation as we know it, just writing out balanced chemical equations. And we can turn this into a complete ionic equation where taking the soluble ionic compounds, splitting the ions apart, because that's actually how the ions would exist in solution. It's not silver nitrate. Solution is not a silver and a nitrate still bonded together. In solution, it's a separate Ag plus and a separate NO3 minus. This complete ionic equation helps to reinforce which ions are free flowing. The AgCl is a solid, so those ions are still stuck together. But we have a lot of things we can cancel. The nitrate and the sodium on both sides exist in the same way. We don't include things that exist in the same way on either side of the reaction. We call those spectator ions. And once we cancel out the spectator ions, we get our net ionic equation, which is really showing me what is actually going on here. If we look at this reaction, there's one main change, but a lot of stuff on the side that's not changing. The net ionic equation takes away the stuff that's not changing, the stuff we don't care about. I don't care nitrates in there because it's not doing anything and it's not changing. And I don't care about Na+, it's not changing in any way. I care about the change that's going on, which is a silver ion combining with a chlorine ion to turn into silver chloride solid. The last bit of reaction writing we looked at was organic reactions, for chemical anyway. And the 3 we focused on was substitution, addition, and esterification. A substitution reaction is when we have one atom in a molecule that's substituted for a hydrogen atom in a saturated hydrocarbon. So I'll give you the example. Do a simple example with ethane. Let's say we have Cl2. So I have a saturated hydrocarbon. The only way this reaction can go is substitution. All the carbons have the number of bonds they should be making. So one of the chlorine atoms in this molecule is going to substitute for one of the hydrogens that's already there. And we're going to create chloroethane. And then the other chlorine atom is going to bond to the hydrogen that was taken off and make HCl, right? So this molecule can be any of the halogens. It could even be HBr. The bromine would substitute in that case. But that's a substitution reaction. Addition is when I have an unsaturated hydrocarbon. So let's take ethene. Let's add the same thing. Let's add Cl2. Now I'm not going to get a substitution. That pi bond in the double bond is weak, right? So it's going to break. And it's going to allow both chlorines to add to the molecule, right? So where this can be thought of as a sort of a replacement, this is more of a synthesis reaction. I get dichloroethane in this case. And then esterification is the more difficult of the 3. Remember, esterification, where we take an alcohol I'm going to draw ethanol here. And an acid, I'm going to use methanoic acid just for convenience. And we add those together, and this is a dehydration synthesis. So remember here, the OH from the acid and the H from the alcohol break off, and they form H2O. And then what is left over, so here's what's left over from the alcohol. And here is what's left over from the acid. They connect together and they form an ester. I see this functional group here is an ester. So now I went from having butanol, I went from having ethanol and methanoic acid to having ethyl methanoate. So the name of the ester, remember, comes from the acid and alcohol that we use to make it. The alcohol is named first, and then the acid, changing it to YL and O8. That took us to the end of chemical reactions, but we did spend some time at the end of the chapter as sort of an epilogue, if you will, to look at some changes that are not considered chemical. If it's not considered chemical, it's considered nuclear. All of the chemical reactions and all of the chemical changes involve valence electrons in some way, shape, or form. But in nuclear reactions, we're not looking at valence electrons. It's not the valence electrons changing. It's the nucleus of an atom changing. Nuclear reactions are different from chemical reactions for the reasons we went over in class, and I just copied and pasted the table here, so you should know those important differences. Some of the important radioactive particles we looked at are here: alpha, beta, positron, proton, neutron, gamma. Radiation is nothing more than a particle or energy that a nucleus is giving off to change, right? And why would a nucleus want to change? Well, back in atomic structure in chapter 3, we looked at isotopes, and that the ratio of protons to neutrons determined whether an isotope was going to be stable or unstable. If the isotope's unstable, it's going to change to become stable, and it changes by undergoing a nuclear reaction or a transmutation. Transmutation is just when the nucleus of one element changes into another, and it's going to do that by giving off one of these radioactive particles. Alpha, beta, gamma are sort of the main ones that you should know in terms of their charge, their mass, how they would interact, their penetrating power. This diagram is showing us how, if we had each of these particles going through an electromagnetic field, how they would interact, right? Beta is negative, so it's going to attract to the positive side. Alpha is positive, so it's going to attract to the negative, where gamma is just going to go straight through because it's not charged and it's not even mass, it's just, energy at that point. If we were going to write a nuclear reaction for a decay, this iron-55 is undergoing beta decay. And what we should do is have a periodic table handy for us to use. I'm going to grab mine here. The iron-55, that's the specific isotope. We're going to need the atomic number of iron, which is 26. If it's undergoing beta decay is really a neutron turning into a proton. And when the neutron turns into a proton, it also turns into a beta particle, and the beta particle comes flying out. And if a neutron's turning into a proton, in this case, the mass is going to stay the same, but the atomic number is going to increase by 1. That turns it into cobalt, right? We could find that information out on the periodic table in terms of the symbol. We can check that our work is correct by making sure the atomic numbers, or the bottom numbers on either side, add up. 27 minus 1 gets us 26. 55 plus 0 gets me 55. But understanding what the overall process is going to be, that's important too. So beta is a neutron turning into a proton in addition to a beta particle. For rubidium-87, rubidium has an atomic number of 37. It's turning into strontium-87, right? So we have that there. What decay would it have to go under to do that? Well, the only one that makes sense is beta decay again. Right? The only way for its mass to stay the same and its atomic number to increase would be if a neutron is turning into a proton and beta particle. The proton stays in the nucleus, the beta particle comes flying out. So let's just practice last couple of examples here for this video with alpha, beta, and positron decay. So uranium-238 undergoing alpha decay. The atomic number for uranium is 92. If it's undergoing alpha decay, we can represent an alpha particle using that symbol or using this symbol, doesn't matter. If it's 2 protons and 2 neutrons, it is a helium nucleus, but we can use either symbol to represent it. If 2 protons are breaking off of this nucleus, it now has 90. And if 2 neutrons are also breaking off, then the mass is going to decrease by 4, because each neutron has a mass of 2 and each proton has a mass of 2. So we're losing 4 mass units. So this is going to decrease to 234. And then we consult the periodic table to see what has an atomic number of 90, and we get thorium. So uranium-238 turns into thorium-234 after undergoing alpha decay. Other terminology we looked at was like the uranium-238 would be the parent isotope, and the thorium-234 would be the daughter isotope in this case. If potassium-38 is undergoing beta decay, we're going to get same mass, but the neutron's going to turn into a proton. So we have one more proton in the nucleus. The atomic number changes to 20. That's calcium. And then positron decay. Neon-19 undergoing positron. A positron is essentially the opposite of a beta particle. It's a positive beta particle, right? Positron. And in this case, the mass is going to stay the same. But a proton is turning into a neutron in this case. So we're actually losing 1 proton. The mass changes from 10 to 9, or the atomic number, excuse me, changes from 10 to 9. Mass stays the same. If I'm losing 1 proton, but it's turning into a neutron, I'm losing 1 AMU and gaining 1 AMU, so there's no net change. We have the neon-19 turning into fluorine-19 after the positron decay. Again, you can recap the differences between the chemical and nuclear reactions. Those are important. But this brings us to the end of Chapter 6, which was chemical reactions with the addition of nuclear reactions at the end, just to compare and contrast how chemical reactions are different from nuclear reactions.